Hello and welcome to the third lecture of the IUR summer course. So today we're going to be discussing multivariate polynomial optimization. So as a recap, in the last lecture we learned how to find the global infimum of an unconstrained univariate polynomial. We presented a lift and project approach, then we presented a sum of squares approach, and then we showed that they are showed how they are two sides of the same coin and provided global optimality proof. In this lecture, we're going to learn how to find the global infimum of a multivariate polynomial subject to polynomial inequalities. So first we will present the moment approach due to Lasserre. Second, we will provide conditions under which one may extract global minimizers, so from a polynomial optimization problem. And we're going to give a full proof in the univariate case. And lastly, we're going to construct the moment sum of squares hierarchy of convex relaxations. So recall last time we saw this proposition, which is that the global infimum of an even-ordered polynomial is equal to the optimal value of a convex problem, and that you can do that by looking at the dual of this convex problem, and it's the sum of squares program, which we saw was none other than a reformulation of the non-convex problem. So effectively, minimizing a univariate polynomial is basically a convex problem in this sense. So what we're going to see now is how do we tackle the multivariate case, and for that we're going to use the moment approach proposed by Jean-Bernard Lasserre. And so the idea, so remember we're trying to minimize some non-convex objective. So let's say here, let's just restrain ourselves to the interval 0, 1. And so in a standard, or like the more traditional approaches for solving or attempting to solve this kind of problem, you would take a variable, say in the middle of the set, and then you would use local information to try to get a better point. And so typically then you might end up here at this local minimum. And well, these methods really are trying to cancel the gradient or find stationary points. So you might find this point, you may also find this point, but so yeah, so you have no guarantees. And so the way that I like to view the this moment approach is that instead of having a punctual variable, the variable actually becomes a measure. And so the idea, you can view this as a weighted average. And so now when you evaluate your objective, you're using all the values of the function. And so then you have kind of hope of finding the global value because you're actually using all the values. It's not just something local. And so this kind of weighted average with respect to this distribution here that is supported on your feasible region, basically this is basically the integration of f with respect to that measure. And so if you have a weighted average, if you want to minimize the weighted average, then you should put all of your mass, all of your weights should be on the lowest values. And so in fact, the optimal solution to this reformulation with measures is actually the Dirac measure at the global solution here. And so you can see the variable was this distribution mu, this probability distribution on the interval. So it has mass equal to 1. And if you put all the mass here, then you minimize this integration. It's equal to the optimal value. And so this is nice because we basically just reformulated the problem. But so now we're in an infinite dimensional space. So remember in the first lecture we saw this idea of like you have a problem, say like 4 variables that's non-convex, and then you can put it in a higher dimensional space, and then you hope to make it convex or linear, or And here what we're saying effectively is that you can basically, if you're allowing yourself to go to infinite dimensions, then you can get your problem to be convex, linear. But so the issue is that this is an infinite dimension, and so sure, we've convexified it in infinite dimension, but we need to somehow get back to finite dimension. And so the way that you can do that, and this is the moment approach, is if you assume that the polynomial and the constraints, that everything is actually, all the functions are polynomials, then you can actually express so here the integration with respect to mu, the objective that you have, you can express it, so f is a polynomial, and then you can swap the integration and the summation, and you get this expression here. And so what you see is that, in fact, everything depends on the moments with respect to the measure. So that's what the definition is you integrate a monomial with respect to the measure, that's the moment, the alpha moment of the measure mu. One thing that's nice, and that kind of, as a first step, kind of you can see like a justification for this approach, is that basically by the Weierstrass theorem, a measure is characterized by its moments if it's supported on a compact set. And so it suggests that maybe we can do something when the feasible region is compact. That it seems legitimate to, instead of optimizing over this measure, which is kind of a very abstract idea, maybe we can optimize over its moments. And that's a little bit less abstract, but there's still all the power is possible. There's still an infinite kind of number of variables. But what we can do is we can just truncate. So we can say, let's take the moments all the way up to order, like, say, 3, and try to solve that. And then, if that doesn't suffice, then we could try to solve for all the moments up to degree higher, degree 4, and so on. And so then we're going to get this hierarchy of problems. And so these pictures, what they're suggesting, and there's actually something we can make very precise here, is that the global infimum of a polynomial optimization problem, so that is we have infimum of f of x subject to x belongs to k, which is defined by polynomial inequalities, g I of x. So k is referred to as semi-algebraic set. And so the infimum is equal to the optimal value of the convex problem, as follows. So you do the minimum over the finite Borel measure supported on k of the integration of the objective with respect to the measure, and subject to the mass of the measure should be 1. As I said, it's like a probability distribution. The mass is 1, and it should be non-negative. Okay. So notice the parallel with proposition 1. There is something that we'll understand better later, but you can see the parallel that we have this constraint equal to 1 and this non-negativity constraint, just like in the univariate case. And so precisely here, so yeah, MK is the set of finite Borel measures on K. And as I mentioned before, it's reasonable to actually assume that K is compact. And so when K is compact, Borel measures are actually easy to understand. So you actually do not need to be well-versed in measure theory. And I'm going to actually show you that with more elementary tools, you can perfectly understand what we mean by this. So in fact, Borel measures are referred to as Radon measures when K is compact, and we're about to see right now some some definitions and some notions that make it perfectly understandable, just basic tools. So first, let's consider this definition 1. So let's see KR denote the set of continuous functions from a compact set K, which is a subset of Rn, to R. And we can equip it with the infinity norm, so the supremum over the feasible set of the absolute value of here this 5x. Okay, and we can define so CKR prime to denote the set of linear functions that goes from the CKR, which is the continuous functions, to R. Okay, this is sometimes referred to as the algebraic dual of the set, this prime. And so, for example, the Dirac at x belonging to k belongs to this algebraic dual, and it is actually defined. This very rigorous. It takes functions that are continuous from k to r, and it outputs the value of the function at a given point x. That's a fixed x. In fact, this function, not only is it linear, so if you take phi, you take some linear combination of phi, then the output is obviously going to be, it preserves the operations of multiplying by scalar and addition. But in fact, it's also a little bit stronger. It's continuous, because if you take the modulus of the output of delta x, Dirac evaluated at phi, it's exactly equal to 5x, which is with this supremum definition, the infinity norm is going to be less than the infinity norm. And so we have continuity of the Dirac, and so we actually can consider the set of functions that are continuous in this algebraic dual, which is actually sometimes referred to as topological dual. And so a consequence of the Riesz representation theorem is that the set of continuous functions in that dual set, it can be identified with the set of finite Borel measures on the compact set K. So now you know exactly what Borel measure on the compact set K means. It is exactly with the two definitions above. It's the functions that are continuous and belong to CKR prime. So basically the topological dual of the continuous functions from K to R. So I hope that you're no longer scared to talk about measures, because really that's all we're going to need, because as I said, we can assume compactness. It's very reasonable for our purposes, for the context of optimization. And so let's actually have a look at proposition 2, now assuming that K is compact, and let's try to understand, let's disentangle what is going on here, because now we understand fully what is meant by all of these notations. So the measure mu, from in light of those definitions, we can view it as a continuous function in this dual set. Okay, and precisely the constraint that it should be non-negative, it means that for all phi, that is in the continuous functions from K to R, it holds that so if it's non-negative on K, then it should be that the measure mu applied to phi, it should be non-negative. That's just intuitively what it should be. So basically the measure is non-negative means that if it takes a non-negative function, it should output non-negative value. So I think it's fairly intuitive. And one example of a non-negative measure is given by the Dirac measure. If you have x belonging to the feasible region K, then the Dirac measure at x is non-negative, since for all phi, if this is true for all y, then in particular for the x that is fixed, then it is going to be non-negative. Okay. And so speaking of Dirac, so for this first constraint, observe that the Dirac in 1 is equal to 1, where 1 is the constant function on k, constant equal to 1. And so typically, so here what we have, we can conclude that the Dirac, for instance, it satisfies both of our constraints. So it's feasible for this convex problem in the box here. The Dirac measure at a point x, so x is a fixed feasible point for x, for belonging to k. Okay. So in addition, notice that the objective function evaluated at the Dirac, so the integration with respect to the Dirac for f is equal to, just by definition, is equal to f of x. Okay, and this right here provides the fact that the convex problem, it provides a lower bound because it has at least something that is feasible and that is giving you a value that is equal to, it can let's see, since we can do this for all x, that means that the infimum for the convex problem is going to be less than or equal to the infimum for the non-convex problem above, basically. Okay, and so now, what about the converse? So basically, we have the lower bound, but is it tight? That's the question. And so let's define f opt to be this infimum. Okay, and so if we take conversely, so we're going to try to show that the convex problem, its value is actually equal to f opt. So we showed it was inferior, less than or equal to. Now we want to show the converse. So take a feasible measure here. So since it's non-negative, and that by definition of f, the optimal value, it should be that f of x minus the optimal value is greater than or equal to 0 for all x and k. And so again, just applying the definition of non-negativity of the measure, it means that this here should be non-negative. Okay, and so now since mu has mass equal to 1, so actually we have that the integration with respect to mu is less than or equal to the integration of f opt with respect to mu from the above. And then here we can just factorize. And so now this is the mass, and the mass is equal to 1, so we just get f opt. And so what we find is that for any feasible point for the convex, any feasible measure, the objective has to be greater than or equal to f opt. And so therefore the optimal value, the smallest integration you can make with respect to f, has to be greater than or equal to f opt. So we've just shown the converse. So it has to be that the f opt is equal to this infimum here. And so basically this proves the proposition. Okay, and so while it may have looked a bit daunting with these kind of measure theoretic concepts, I think you believe me now that just we assume compactness, then we really fully understand everything. And so this is what the pictures that I showed you earlier were suggesting, and this is a formal, like rigorous proof of that idea. Okay, and to get a bit more intuition, so if the global minimizers of the polynomial optimization problems are x1 through xs, you can have multiple global minima. Then the set of optimal solutions to the convex problem, to this relaxation, just to the convex problem, this convex reformulation in infinite dimensions, is going to be given by essentially taking all the convex combinations of the Dirac measures at the global minimizers. Okay, and so in particular, you could take the mass to be 1 at one Dirac and have the mass 0 at all the other Diracs. So you could have one of those global minimizers. Just that Dirac would be a solution to a global solution to this problem, where you could take, any uniform weights for all the Dirac measures. So let's see how this proposition can help us on this example. Let's try to illustrate it. So remember, this is the same example we looked at in the previous lecture. It has a local minimum, it has a global minimum. And let's convexify this non-convex problem. Let's convexify it using measures. So using proposition 2. So just to go back, we're just going to write this box here for our problem. So remember, we have the integration with respect to the measure. We have mass equal 1, non-negative. So we're going to just write that. So integration with respect to the measure, so integrating the objective with respect to the measure, mass equal 1, and non-negativity of the measure. Okay, so we can expand. I just expanded the objective right here. Then we can basically just roll out the definition, so the non-negativity of mu of the measure. And so what can we say about that? So that means that in particular for any polynomial p, the integration with respect to p squared should be non-negative, right? Because p squared is non-negative, it's a square. So that should integrate to something non-negative. Okay, and so for instance, let's consider the notation, this following notation. So basically, let's just consider polynomials of degree less than or equal to 2. Okay, and so this should be true, right? And so we can compute the square. It comes up here, so let's compute it. So this is what we get. We expand sum over I and j, and now we can, plug that in. So we plug that in here, right? And now we can swap integral and summation, and we can also factor these out. And now what we have here is really a positive semi-definite constraint. So if you view this as the term of a matrix, the term ij of a matrix, then this is none other than a positive semi-definite condition on a matrix. And so we can write it like this. This is what we did in the last lecture, this kind of notation here. And so to make it, here, since the indices are all from 0 to 2, I can actually explicitly write this matrix. And notice how here we've written everything in function of the moments of mu. So this is just like I was showing you on the picture. If we assume, that the objective and the constraints, so here there are no constraints, but if everything is polynomial, then in fact, when you use this convexation with respect to the measures, then you end up with only the moments of the measure. So that's what we have here. And so we could just define, we could basically, this allows us to basically lift the problem. We define these variables that correspond to the moments, and we just substitute. And ta-da, we're back to, this is what we had shown in the univariate case by completely different considerations. We had done very pragmatic, trying to write the non-convexity in the objective. We wrote it as non-convex constraints. Then we tried to figure out how can we remove the non-convexities. We did something just, very special for that problem. But yeah, it turns out that there's actually a more fundamental concept behind it. And so here we're seeing it. This idea of convexifying with measures actually leads us naturally to this convex relaxation. Okay, and so here the hope is that when we solve this problem, this convex problem, is that there should exist a measure that represents these what we call pseudo moments, essentially, because we would like them to be moments, but here they're just variables in the problem. They're just kind of, they don't have any more constraints than those that are written here. Would like this to hold. And remember that we had solved this in the last lecture using MATLAB, and we had found like the sequence of powers of 2, and in fact, what this means for us is actually the Dirac measure at 2. That's what we actually found. So if we reinterpret what we did, in fact, what we did is we convexified using measures, and then optimized over these pseudo moments, and then when we solved for them, it turned out that they could be represented by the Dirac measure at 2. And so that proves that, thanks to the proposition 2, that 2 must be a global solution. Okay, so what I'd like to do, this is one of the problems in your problem set, is to give a sufficient condition on these pseudo moments. So say you optimize, use MATLAB or whatever, you find a set of optimal pseudo moments y, and we would like to show that if this moment matrix here has rank 1, so these pseudo moments, if they form, if this matrix has rank 1, then there exists some x such that these pseudo moments are actually the moments with respect to the Dirac measure at x. So this is very important. This gives you a means to check. So you take an optimization solver, you solve this convex problem, and then you can check that that you found the global solution. So not only can you check, but you can also extract it. That's something that we're going to see. You can extract it using linear algebra routines. You can extract this x. You can effectively, find the global solution. So what if the rank is not equal to 1? Does there exist a measure, so a non-negative measure, that represents our pseudo moments? So this is actually a deep question, and we're going to actually pose this problem like more formally. We've been working with this example. Now let's just see in full generality what kind of question this leads to. And this actually leads to the hamburger truncated moment problem. So this is something that was studied a century ago, a little over a century ago. Basically, it raises the following question. So given some real numbers, y0, y1, y2, all the way through y2d, does there exist a non-negative measure such that yk is equal to the moments of that measure? That yk is equal to the kth moment of that measure for k goes from 0 to 2d. And for our purposes, we would like to give some kind of condition. We would like to know when is this true, because it is exactly going to tell us, we solve this convex problem that we had convexified using measures, and these pseudo moment variables, do they contain a global solution, yes or no? And this is going to tell us, this answers this question. And so let's look at this in the first lecture or the second lecture. We had convexified kind of hands-on or hand wavy. We just tried things, and we ended up with this convex relaxation. We just took out non-convexities from the constraints, and this is what we had. And remember, we found this lower bound of minus 1.56. And we had these variables here, these lifted variables, where notice, remember, we had that y1, which represents x, was actually not too far from the global solution 2. And And so now that we look at this list here, which you could view conceptually, you could say these are pseudo moments. They would like to be represented by a measure. So given that the infimum of the problem, the global infimum of the non-convex optimization problem, is 1, based on this here, can this sequence here, can it be represented by a measure? So I'll let you think about it for an instant or two. So the answer is no, and this is by virtue of proposition 2 again, and because we know that so if those variables were represented by a measure, then when you look at the objective should be greater than or equal to the optimal value, which is 1 in this case. So it would have to be greater than that or equal to it. And as you can see here, is actually below. It's with these variables, if you evaluate this, you get exactly minus 1.5677. And so, in fact, no, you cannot represent these here. You cannot represent them. So if you look at the hamburger truncated moment problem, if you were given these numbers here, no, there does not exist a measure. Okay? But you can sense how here it's kind of, it's not so obvious in general. It doesn't seem so clear how we would be able to tell such a thing. And so we're actually going to propose, or I'm going to present to you a solution to the hamburger problem, and it goes as follows. So given some numbers y0 through yd, 2d, there exists a non-negative measure such that those numbers are represented, or they're equal to these moments with respect to mu, if and only if this moment matrix of order d, defined as follows, is positive semi-definite, and either the matrix is invertible, or there exists an index t, non-negative and less than d, such that the rank is preserved between the moment matrix of order t and of order d. Okay, so we're actually gonna prove that now. Before we prove it, let's just see how it applies to our problem here. So actually, if we kind of stack them up this way, the pseudo variables here, the pseudo moments, we can compute its eigenvalues, and we see that there's a negative eigenvalue. Okay, and this is basically the moment matrix of order 2. And since it's not positive semi-definite, it cannot be represented by a measure. So there's just a confirmation of what we were saying earlier. So this matrix here, this condition is being violated by those pseudo moments. Okay. So notice that there is a special structure in this moment matrix, and we're going to make use of that in the proof. So what happens is that the anti-diagonals are actually constant. So here it's all y1s, and it would be all y2s, and so on, and here's all yd's, and so on and so forth. And that's what you call a Hankel matrix. So it's constant along the anti-diagonals. So I invite you as a warm-up to prove that this equivalence holds when y0 is equal to 0. That is to say, so how to do that is you should answer these two questions. So what is y if y0 is equal to 0 and a measure exists? And then what is y if y is equal to 0, the moment matrix is positive semi-definite, and there exists such this condition is satisfied. And so basically, what you can find in both cases is that y is just 0. Like all the terms in y have to be 0 in either case. And so this actually proves that if you kind of intersect this equivalence with the fact that y0 is 0, you see that that equivalence holds. Like the only possibility in either case is for just y to be equal to 0. Okay, and so now let's consider the only if part. I invite you to try and see why should it be that the matrix is positive semi-definite when y is represented by a measure. The rank condition, the other conditions, this being invertible or the rank being preserved, we're not going to get into the details of that, but I will just tell you that this rank condition here, it is related to Chakalov's theorem, which provides an exact quadrature formula. Essentially, it tells you that there exists some coefficient Ci and some real numbers xi, such that for all polynomials, essentially this integration is, you can figure it out by just looking at p at this support, these xi's. This works for any p. So this is actually something that is widely used in numerical integration. But I'm not going to delve too much into the details here. But so the thing that is actually most important for us in practice is this other direction, this other implication. Because this other implication is going to give us a sufficient condition for when we can extract a measure from our pseudo moments, that is the actual practical question that you seek to answer. So you have this convex optimization problem, you solve it, and then you want to know, can you extract a measure? And the question is really about this if part. So we're going to focus on that. So we're going to begin by assuming that that the moment matrix is actually invertible, so this case here. And we're going to show that in that case, M, the moment matrix of order D, can be extended to a positive semi-definite matrix of order, so it's actually a moment matrix of order D plus 1, such that the rank is preserved. Okay, and so what that means is that effectively we can always just assume that this rank condition is satisfied for the purposes of the proof. Because if this is satisfied, then you basically just have to add 1 to D, and then you're going to be in this case here. Okay, so let's actually do that. Let's assume the moment matrix is invertible. Let's do it on a very simple example, and I think this is exactly, the general case is exactly this, but for presentation purposes, I'm going to just take a second order moment matrix. So assume that it is invertible. So we already assumed that it's positive semi-definite. So if an addition is invertible, that means it's actually positive semi-definite. So in other words, so just recall positive semi-definite is equivalent to all the eigenvalues are non-negative. So if you add additionally that the matrix should be invertible, then none of those eigenvalues should, they cannot be equal to 1, so they have to be positive. And that's what this is here, saying that all the eigenvalues are positive. Okay, and so now let's try to construct an extension. So recall this Hankel property. So if we try to do an extension, since we have this constant anti-diagonal, what happens is that this is the additional column and additional row that we're adding in the extension, but this here we don't have a choice. It has to be equal to this y3, And we don't have a choice either here. This has to be equal to y4. So the only degrees of freedom we have really is just on this term here and this term here. So there's really two terms only. So let's compute, this is the determinant. So we can use this, the standard rules on expanding determinants to obtain this here, and then we can expand further. And now, right, we have the beta, we can factorize the beta. And so what's nice here is that we can actually choose alpha and beta. We can always choose it so that it cancels the determinant. And so the reason for that is that here, this is positive semi-definite. So that means that the determinant in particular has to be positive. And so what you really have is you have a second degree polynomial in beta. So beta squared multiplies by something plus beta times something plus some constant. Okay, and then we have alpha multiplied by some positive quantity. And so you can always find, if you take some beta, you can always find some alpha that is going to cancel this whole expression. And so what's nice is that we can extend the matrix while preserving its rank. So recall, this matrix is rank 3. It's full rank because, I mean, it's invertible, so it has to be full rank, and there's 3 columns, so it's rank 3. And this matrix here has a determinant which is equal to 0, and so that means that it has to be of rank less than or equal to 3. But it contains a matrix of rank 3. So in fact, it has to be exactly of rank 3. So we've found an extension that preserves the rank, and in fact, what's kind of a byproduct, a very nice byproduct is that when the rank is preserved, we actually get positive semi-definiteness to be preserved for free. Okay, and so we're gonna have a lemma to show that right now because this is the only missing piece, right? So we wanted this extension to preserve the rank. And so this follows directly from lemma 1. So consider a matrix A, which is positive semi-definite of size n, and consider an extension. So this is just like here another column and here another row. So B is on Rn, C is on R. So if the rank of the extension is equal to the rank of the original matrix, then the extended matrix has to be positive semi-definite. That's exactly what we want to prove. And it's actually very simple. The fact that the ranks are equal, what that means is that B should be a linear combination of the columns of A, and so that's exactly what I'm writing here. So B is equal to A times some vector W, and likewise C should be the same linear combination in function of beta transpose, B transpose, and so that's what you see here. And so then we can just take the extended matrix, we can substitute, so B by A times W, B transpose, sorry, there's an A missing here, by W transpose A transpose. And then here we take C is B transpose times W, and then B is A times W, so you end up with W transpose times A times W. And so in fact, you can factorize this, and so now you have that A is being multiplied by some so the fact that you have the same matrix on both sides means readily that you can deduce that this matrix is positive semi-definite. So now let's go back to our this solution that we're trying to prove to the hamburger moment problem. So now we said if the matrix is invertible, then we actually can deduce that, if we were to take d equal d plus 1, we would actually just satisfy this rank condition. So in fact, we can assume that the moment matrix is positive semi-definite, and we can assume that this rank constraint is satisfied. So that's what I'm writing here. We can assume that for t, we have that this is true, okay? And since the extended matrix is positive semi-definite, we can write it in Gramian form. So in other words, each term in the matrix is none other than the inner product between a set of vectors, and the vectors live in here. This is the common rank. Okay, and so just, this is the notation for the inner product. And we have that those vectors that form the Gramian, they span exactly the space of dimension R. Okay, and because the rank is preserved, it's actually easy to show that Vt plus 1 is a linear combination of V1 through Vt. Okay, and now thanks to this Gramian decomposition, we can define the so-called shift operator. So it goes from r to the power r to r to the power r, and it takes some element here, and so in light of the above, any element here can be written as some combination, some linear combination of the vi from 1 to t. And so the shift, it means that we just, as the name suggests, we shift the indices by 1. So now it goes, it goes from, so we shift it by 1. Okay, and so so it's called shift because if you apply it just to the vi, it's going to make it v into vi plus 1. Okay, so this thing right here actually should be v index 1. So sorry for that's where the confusion is coming from. Okay, and so we have to check that it is well defined. Okay, that in other words, we need to make sure that for two different inputs of coefficients, it should produce the same output. Okay, because technically you could imagine, if you take an element here, this may, for one element of RR, there may be different coefficients, so say C and C prime, that represent it, but we need to make sure that there's a unique image so that it's actually a function. And so we need to prove this implication. Okay, so let's actually, let's show that. So let's take the difference between these two. Okay, so the difference between these two here, we want to show that if you take the difference between these two, this inner product is equal to 0 for all of these vectors. And since they span the whole space, if you have an inner product with vectors that span a space, they're all 0, then you must be equal to 0. That will prove our point. Okay, so we can expand, we can compute this. So this is very simple, linear algebra. We just, use linearity. Okay, here we use the definition. So this here is, it's the Gramian. This is just the Gramian formula. Okay, and now notice these indices, we can swap them. Okay, and now we can backtrack. This thing right here, we can apply again the inner product formula. And now we basically are making a swap in these indices, which is highly non-trivial, and then we can do it here as well. And basically that proves our point, because this here is the difference between these two, and we're assuming that the difference is 0. So that means that this here is 0, and so that proves our point. Okay, and so it's well defined. So for two given inputs, two different sets of coefficients, the output is going to be the same. Okay, now in fact the shift operator is symmetric. Indeed, if you take S times VI inner product with Vj, by definition, this shift, it adds 1 to the index. Then here you use the, Gramian formula, and here you can swap, and then here again you use this inner product formula, and this is just a definition of the shift, and so you can see it's symmetric. So implicitly what we're using here is the fact that we have a Hankel structure. Okay, and now by the spectral theorem, there exists an orthonormal matrix P and a diagonal matrix D such that S is equal to P times D times P transpose, where D is a diagonal matrix and P is some orthogonal matrix, and we can use this as the notations for the columns. So P1 is the first column, PR is the last column. Okay, and so using the spectral theorem, we got this expression. Now we can plug that in. So this is the general term of the moment matrix of order D, so y I plus j. So this is by the Gramian it's the inner product between Vi and Vj. We can the shift, you can just apply it again and again and again, and then you're just going to end up basically, if you apply it I times to V0, then you're going to end up with Vj, right? So this is applying it I times, so s to the power I. Now if you do s to the power j, same thing. Okay. Now by symmetry, we can put this on the other side, and we get si plus j. Okay. And now by the spectral theorem here, we can easily compute its power. So its power is given here. Okay, and now we use the inner product, the definition with the transpose, and we get this here expression. Okay, and now we can analyze what's going on here. This P times, the diagonal matrix to the power I plus j times P transpose. This is actually none other than you're basically putting the diagonal elements to the power I plus j, not unsurprisingly. So this is showing, turns out now you can have V0, you can put it inside here. It's going to be the inner product with pk, and then V0 here it's going to have an inner product with pk again. So that's V0 inner product with pk squared times the diagonal elements to the power I plus j. Okay, and so that is actually this is none other than, so this term here is none other than the Dirac. So the moment of order I plus j with respect to the Dirac at dk. So that's what I'm writing here. Okay, so if you look at this function of x and you evaluate it at dk, that's exactly dk to the power I plus j. That's exactly what you have here. This is just like looks very fancy, but it's just very simple. Okay, and now if you just factorize, or you can easily swap the integral. Sorry, you swap the integral and the summation sign, and now you found a measure. So now this here is the sum of Diracs with certain weights here, and this is the supports dk. So basically the diagonal gives you the supports, and then the columns here, they're going to give you the weights. And so you can see the general term here of the moment matrix of order D, so yi plus j, is actually the I plus jth moment with respect to a measure. This measure is a finitely supported measure, it's called. So it's a sum of Dirac measures. Okay, and so that proves our theorem. So that is exactly what we wanted to obtain. Okay, so now that we've proven the solution to the hamburger moment problem, now we have a bit of a better understanding of this idea of using measures to convexify our problem to write a convex optimization problem first in infinite dimension, and then in finite dimension, and then in finite dimension we have these pseudo moments. We're not sure if they're represented by a measure, and here we saw in the univariate case a sufficient condition to have a measure that represents them, and therefore to prove global optimality. And so now I want to show you another point of view, just kind of like we did in the last lecture. We had this lift and project point of view, which you can now kind of interpret as this, lifting into this infinite dimensional space, and then solving hopefully in a lower dimension. But we also saw in lecture 1 when we were doing univariate polynomials, we saw there was this dual point of view using these lower bounds and using sum of squares. And so in the multivariate case, you also have this, and so that's what we're gonna show next. Okay, so again here, positive polynomial, we can take a lower bound, and we end up, if you take the function you're trying to minimize minus the lower bound, you have a positive polynomial. So positive polynomials play a key role in this kind of dual approach. And so to formalize this, so if you take f-op to be the infimum, the global value of this polynomial optimization problem, so the feasible set, remember, it's this set K, this semi-algebraic set defined by polynomial inequalities. And so we have a simple observation that if you take any epsilon positive, then it should be that this polynomial here, so f minus its infimum plus a tiny epsilon, should be positive for all k. Right? This is just like tautology, basically, trivial. And so we have that this is non-negative by definition, and so you add a little bit, so it's going to be positive, right? And so you can see that positive polynomials, how they enter the picture. And so we have this very deep result that was proven almost 3 decades ago, called Pütner-Positivteilansatz. And so what it says is that if you have a polynomial, so multivariate polynomial, that is positive for all x such that these polynomial inequalities are satisfied and a ball constraint is satisfied, then you can write f as a weighted sum where the weights have a very specific structure, and they're actually the weights, these sigmas are the weights that multiply these constraints, and they are going to be sum of squares. Okay, so let me show you an example. So say we take x plus 2, and that is going to be positive for all x such that 1 minus x squared is non-negative, right? Because basically x has to be between minus 1 and 1 in that case, and so x plus 2 is always positive. Okay, and according to this theorem, and we check here, we see that x plus 2 is actually written as this square here plus a square times the constraint. So this square is this sigma 0, and this square here is this sigma n plus 1. Okay, and so now we can apply this theorem to this observation that we've made. So effectively, we can apply it to this function here. This function is positive, so we can decompose it as a sum of squares expression. And so that's what we're going to do here. It's positive, so you can write this. You can write this, so you have this weighted sum. So these are sum of squares right here. And these are the constraints, gi. And so we're assuming that you would have one of them being a ball. And so that's where this idea of we need to have a bounded feasible region. And in fact, it's a little bit stronger, right? Because we also need to know a bound. So here I put 1, but you could technically have just any radius, like r, for instance, here. Okay, and so now we can just by making this little subtle change here, what we see is that this here basically corresponds to a lower bound. And this f op minus epsilon is just a little bit below your global value. And basically for any lower bound that's strict, you can always find a decomposition. Okay, so as close as you'd like, you can always find a sum of squares decomposition. And so basically the idea for the hierarchy is just to say, okay, let's take these sum of squares to be of degree bigger and bigger and bigger and try to maximize that lower bound. And we're guaranteed, just because of what is written here in front of you, guaranteed that this is going to converge towards the infimum. We can get as close as we'd like to the infimum by taking sum of squares with degree bigger and bigger and bigger. Okay, so let's introduce some multivariate notation now. We're going to actually show, what I just kind of talked about. We're going to illustrate it on an example. So we're going to do essentially the full-blown moment sum of squares hierarchy. We're going to see what it looks like. So you were minimizing this polynomial, so this multivariate notation. So we're just recalling this monomial x to the power alpha is x1 to the power some integer times xn to the power some integer over some polynomial inequalities. And so for example, if alpha is equal to 2, 1, 0, 1, what would x alpha be? Well, our x alpha is going to be equal to x1 to the power 2 times x3. Okay? Yeah. And also we're going to define the degree of a monomial to be, this modulus here it's just the sum of them all. So here, like, the degree is 3. Okay. So recall from the proposition 2 that was shown earlier in this lecture, this here can be exactly reformulated. It has the same optimal value, so you're just reformulating the problem over measures over this infinite dimensional space. And we're going to really systematically construct it. We're going to basically do convexification using measures. We're going to do it systematically. So if mu is feasible, this measure is feasible for this problem, so in other words, it has mass 1, it's non-negative, then we can write the following, so mass 1, and it should be that, if you take any polynomial and you put it to the power 2, that p squared is non-negative, so if you integrate with respect to mu, it should be non-negative. Mu is non-negative, that's this constraint. And also we can do this for, integration with respect, we can integrate p squared times gi with respect to mu. Indeed, gi is non-negative on the feasible set k. And, that is, so if you go back to the definition, mu being non-negative means that for any function that is non-negative on k, the integration with respect to mu should be non-negative. So again, that's what we're using here. Okay, and so if we use this polynomial p, so we use this multivariate notation, polynomial notation. So it's the sum of these coefficients times these monomials. So these are multivariate monomials. Okay, and we do like we had done before. So we go ahead and expand this. So you expand this out. This works just like in the univariate case. You just add up these are multivariate monomials, recall. So this is basically integer. These are like two vectors of integers that you add up together. Okay, now you can swap summation and integral, and you recognize here you have this positive semi-definite condition. And so you have these two matrices that should be positive semi-definite. So these matrices are indexed by monomials. Just mind that these are the indices. So instead of having I and j, now we have monomials up to a certain degree d, and here up to another degree. So this is the ceiling of the degree divided by 2. Okay, so we get these positive semi-definite constraints, and now we're just going to try to express this gi of x. So if we express it as just some polynomial, Here we're going to get and swap the integration and summation, and essentially the point that we're trying to get at is that we want to express everything in function of moments, and we have just done that. And so, in fact, the objective, the integration with respect to mu, you just, this would I've already shown you. You can swap the sum and the integration, and you get, so everything now is in function of moments. So the objective, all the constraints are in function of the moments of mu. Okay, so we can just replace them by these lifted variables, these pseudo moments, y variables. Okay, now we have this leverage. We have d, which kind of chose arbitrarily, and now we can take d to be bigger and bigger and bigger, and so we get this hierarchy of convex problems. Okay, we've obtained this convex relaxation. Yeah, right. So we minimize. Basically, in the objective, we have this. Basically, you linearize the objective with these pseudo moments, and then you have these. This is trying to make the measure 1, the mass 1, and this is these are trying to. So essentially, what these do is they try to make the moments these are pseudo moments, right? So they don't necessarily need to be represented by a measure. We hope that they do, and what these constraints are going to do is they're going to try to make it represented by. We're going to try to make them. It's going to try to make them the pseudo moments represented by a measure, and that measure be supported on the feasible region K. It's going to try to satisfy all these constraints. That's what this is doing intuitively. Okay, and so this is actually, you have these notations that are standard. So this is the Riesz functional moment matrix and localizing matrix for the reason that I just told you. So this we already discussed. This is I just introduced. And this here is the localizing matrix, because it's trying to make the support located within the feasible region. The sum algebraic set K. Okay, so so what would happen is actually here, if you were to write this for all d, like you write for d equal 1, d equal 2, d equal 3, write all these constraints for all d, you would have an infinite number of constraints. And it turns out that if you did that, then you would be guaranteed to have global optimality. So in other words, it would make the y be represented by a measure. And this is what the next result is saying, that if you put all the constraints, so basically if you're an infinite dimension, then you can always extract a measure. So in other words, this problem here is equivalent to this problem when you take it for all d. You take all the constraints possible. Of course, in practice, we don't want to do that. In practice, we want to only do like d equal to 3, for instance, and just compute that and hope that we can extract that. And so that's what we'll see right after. We're going to see what about when you have like a finite d, when can you extract? So this is if you have infinite, you have all the possible d's. And so what this is saying is that if one of the constraints defining K is a ball, then we have the following: given some real numbers that are multi-indexed, there exists a measure, a non-negative measure that represents these numbers, so that the numbers are actually the moments with respect to a measure. And this is true if and only if, basically, we have feasibility. So in other words, moment matrix is positive semi-definite, localizing matrices are all positive semi-definite. Okay, and you can see kind of, this is actually a dual, there's like a primal dual perspective on what I just said about sum of squares, where you needed to have a ball constraint, and this here. So this is what I'm writing here. This is equivalent to Putnow's Positivstandssatz that we saw regarding sum of squares. Okay, but of course, in practice, what we're interested in is the truncated moment problem. So we want to know when we can't compute when we have an infinite number of constraints, but when you have a finite number of them, we can compute it. So that's what this is answering. So assume that, yeah, we just have to make a little assumption here that at least one of these constraints is not a constant polynomial. So it's really, you know, not asking a lot. So given some multi-indexed numbers, now a truncated sequence, there exists a rank md minus dmy atomic measure mu that is non-negative, supported on k, such that, so y alpha is represented by them, they're the moments, if and only if we have the moment matrix is positive semi-definite, the localizing matrices are positive semi-definite, and the rank is preserved. Okay, so just to, let's try to unbundle this. So T atomic means that it's a linear combination of T Diracs. So if you recall the solution to the hamburger moment problem, remember we had proven in the end for the proof, we proved that we were able to exhibit a measure that was a sum of Diracs. And this is what this is saying here. That you have this, you can guarantee that. And you can see kind of the analogy with what we were doing in the rank 1 case, that you have to have positive semi-definiteness of the moment matrix. That's the same thing. You have to have some rank condition that should be, the rank should be preserved. That's the same thing as the univariate case. But now we have all these other, right, we have all these other constraints. Anyway. So we're not going to prove this, but now I'd like to illustrate, because these notions I realize are a little bit abstract. So let's illustrate all of this on a concrete example. So multivariate polynomial optimization. You have an example right in front of you. So here's two variables, minimizing this polynomial of degree 3, function of x1, x2, and subject to this ball constraint. Okay, so I've represented this function here. And we're optimizing over basically a ball within here. And what we have is basically right here, I believe it's near the origin, we have a local minimum. It's something that, with a local search method, with traditional method like gradient descent, you could get stuck there. The global solution is actually here. And so it's actually quite spectacular. What we're about to see is that we're actually able to overcome this fact that you could get stuck here normally, and we're going to find the global solution, which is right over here with the blue, dark, deep blue values. Okay, so I write this moment this moment approach, and what you get basically this convex relaxation in function of these pseudo moments. So I just linearize the objective. So every monomial, I just write it as a y variable. So notice here that the y have, they're multi-indexed. They have two indices, and that's because we have two variables. So like let's say this term here. So it's it's actually x1 to the power 0 times x2 to the power 1. So that's why you see this y0, 1, and this is the coefficient. Likewise, say here you have x1 to the power 1 times x2 to the power 2, so that the corresponding term is y11. Okay, and so if you write out the moment matrix of order 2, this is what you're going to get. And now if you write the localizing matrix, corresponding to this ball constraint, this is what you get. This is the localizing matrix. And so I've chosen this example nicely because it has a ball constraint. So we know we're guaranteed to have convergence if we were to do, take bigger and bigger convex relaxations. We're guaranteed. But it turns out that here you don't need to go very high, and we can confirm it. We're going to confirm it. But so let's compute it. So we take a semi-definite programming solver. We solve this problem, and what do we get? We get this optimal value here of minus 0.9843. And the moment matrix, you get these numbers. And if you compute the eigenvalues, you find that they're all non-negative. Okay, and you find that it is rank 1. So if we just go back to this theorem here, we did this for a purpose. Let's check. So this condition 1 tells us that this should be positive semi-definite, and it is. We just checked. The rank, the fact that the rank is, so you can also check that this is true. And the fact that the rank is preserved is obvious here because the rank is 1. So it's obviously true. And so we're guaranteed to have a representing measure for our pseudo moments, for those y variables that have 2 indices. They're represented by a measure. And so this guarantees global optimality. And in fact, you can look at the optimal value here, the minus 9.98, and you can see on the picture here that indeed this blue region is right next to minus 1, right over here. Okay, and I just wanted you to let it sink in, like how spectacular this is, because there is a local minimum here. That local minimum has a positive value. It's around, a little bit above 0. And if you took gradient descent, and actually you could try it on this if you want, go ahead and code it at home. Do like a projected gradient, initialize a point here or something, it will get stuck here. But, with all the stuff that you just did in these 3 lectures, all these, this gymnastics that you did allows you to overcome this and to actually find the global solution. And so this is the kind of approach, these techniques that were applied in the first lecture to solve large-scale power grids, to optimize large-scale power grids. And there's a lot of technicity to make this whole machinery work, because as I said, you have to exploit sparsity, you have to exploit symmetry, and I invite you, if you want to know about that, to read. You can go to my website and you can read some papers about that. It's quite sophisticated, but I think it's obviously I think it's fascinating. This optimizing electric grids using the Lasserre hierarchy. And just want to finish off by reminding you that I have made 10 problems for you to solve. So there's a problem set that is attached, and I've really handpicked them from the literature. These are, I think, the most significant problems that some of the most significant problems that you can try to solve, and they're all relatively, the difficulty is not very high. I purposely chose them so that they're doable. And some of them are a little bit trickier, but you have the correction, you have all the solutions. So yeah, I hope that you enjoy doing them, and yeah, feel free to contact me for any questions or suggestions. Thank you very much.